Welcome to lecture series on digital electronics under EPG Pathshala. This module is dedicated to understand the system applications. So far we have discussed the Boolean algebra, combinational circuits, sequential circuits, state machine design and several other cases. Whenever we talk about utilizing digital electronics as a tool for variety of systems, we need to talk about how the information is gathered by the digital system, how is it processed and how it could be used for displaying it. There is one more application that is required, that digital system can be used for controlling variety of systems. So, naturally we need to deal with some of these simple applications, right from smart TV, maybe smart mobiles, or there could be several applications in industrial process applications. If you talk about a simple printer, in a printer we need to control precisely the print head as well as the movement of the drum. So, naturally the drum can be rotated through a precise angle to print a specific line. Now, such kind of a system requires a stepper motor. So, the first application what we have considered in this module is stepper motor control application. Stepper motor is a special motor which needs a precise control through a precise angle, and that requires a digital system. We can use combinational as well as sequential circuit to implement a stepper motor controller system. Let us move on to the second application, wherein we would be discussing vending machine example. Now, in a vending machine, when we input certain number of coins to the vending machine definitely delivers some kind of a product to the user. Maybe it could be a sweet dispensing machine, it could be newspaper dispensing machine, it could be Coke dispensing or any other application we can think about. So, that requires some kind of a digital system. So, we would be focusing more on how the vending machine can be designed, or we will be understanding several blocks present therein. The third application, which is focusing more on designing some kind of tablet filling machine. When we talk about pharmaceutical industry, we need to really fill the tablets into the bottles. So, naturally the first step that we require is counting the number of tablets, putting these tablets under one bottle, then counting the number of bottles and pass it on to the packaging. So, basically such kind of a system requires a conveyor belt system, conveyor control systems, counting the number of tablets and several other applications. When we talk about our day to day traffic light systems, definitely depending upon the complexity of the road, depending upon the junctions those are present, we need to think about how the traffic light system could be designed. In this application, we will be treating almost all applications as a simple example of finite state machine. Every application is treated as a state machine and will identify the number of states those are required to implement the system. We will design a state diagram, we will find out how many flip flops those are required for the implementation. We will provide some feedback with the help of some combinational blocks. Based on the present input condition and the present state, we will be designing the next state for the application. We will be finding out definitely input and output Boolean expressions to design some of these cases. So, let us talk more about the system applications in this module. Let us now get familiar with the learning objectives. First, to understand stepper motor control application, to study the vending machine application, to learn the traffic light control system, to know the tablet filling system application. Let us begin with the first case study of stepper motor control circuit. Let us now consider a case of motor used in a printer. The paper outflow does not stop in time. It is possible to lose paper every time we start and stop. Therefore, it is needed to wait for the motor to pick the speed, and due time the paper is lost. This is unacceptable for most of the control systems. So, to solve this kind of a problems, we use stepper motors. The stepper motor is called so because the rotation of the shaft is in the steps, which are different from DC or AC motor. In other motors, the speed of rotation, the stop angle are not in complete control unless necessary circuit is inserted. This non-control is present because of moment of inertia. Consider a DC motor. Once it is powered, the speed of motor is depend on the power supply. Now, if the power is turned off, the motor does not come to halt immediately, as it will have moment of inertia, it stops slowly. A stepper motor control system is a circuit that provides the necessary current and voltage to a stepper motor so that it has a smooth operation. The stepper motor is a kind of DC motor that rotates in steps. In a simple DC motor, the basic difference between a simple DC motor and a stepper motor is that through a stepper motor, it is possible to precisely position the control with the help of digital control system. Let us consider the architecture of stepper motor. The stepper motor does not work on constant supply. It can only be worked on controlled and ordered power pulses. There are two types of stepper motors, unipolar and bipolar stepper motors. As shown in figure, in a unipolar stepper motor, there are 4 coils. These coils are driven by pulses and other ends of the coils are grounded. A shaft is attached to the rotor, whose rotational angle need to be controlled by the digital control circuit. A stepper motor controller consists of synchronous counter and a current amplifier cum driver. A stepper motor rotates precisely by synchronizing the pulse signals from a controller, which are given through the stepper motor driver circuit. A stepper motor driver is a circuit that makes the pulse signals from a controller and converts it into stepper motor shaft rotation. The synchronous counters can be used to a practical situation like driving a stepper motor. A stepper motor is a motor that rotates in a steps, typically 18 degrees per step rather than a continuous motion. The magnetic coils or windings in the motor must be energized or de-energized in a particular sequence to produce a stepping action. Digital signals are normally used to control the current in each coil. The synchronous counter has direction input D to decide the direction of rotation of the stepper motor. If D is equal to 0, then the stepper motor shaft rotates in a clockwise direction, and D is equal to 1 results in anti-clockwise rotation. The outputs of the counter produces 4 outputs: A complement, B and B complement. These outputs are used as inputs to the current amplifier cum driver. A clock is fed to the synchronous counter. A frequency of clock pulses can decide the rate of rotation. If D is equal to 0, then counter should be designed to generate the sequence of steps as shown in the state table. The sequence of binary numbers are 00, 01, 11 and 10. This sequence is required to be repeated all over again and again for clockwise rotation continuously as shown in the state diagram. For anti-clockwise rotation, when D is equal to 1, the counter generates 00, 10, 11 and 01 sequence. This sequence must be repeated all over again for continuous rotation. Let us now talk about the applications of stepper motor. Stepper motors are used extensively in situations where precise position control is needed. For example, positioning read or write head on magnetic disk. Second application, it is normally used in controlling the print heads in the printer. It is also used in controlling various pieces of robots maybe the arm control, gripper control, and so on. Let's now talk about another case study, that is vending machine. A vending machine is an automated machine that provides items such as sweets, snacks, tea, coffee, and beverages to consumers after money is inserted into the vending machine. It is a machine that dispenses some product at the output when money is inserted into the slot automatically. Vending machine that provides less common products compared to traditional vending machine are also designed and distributed in a consumer market. The common vending machines are for dispensing change of currency, food and snacks vending machine, candy or sweet vending machine, newspaper vending machine, stamp vending machine, and ticket vending machine. Let us consider a case study of designing a controller for simple vending machine which delivers a packet of sweets after 3 rupees are deposited. There is a single coin slot for 1 rupee and another slot for 2 rupees. If excess money is deposited, the sweet is delivered but no change is returned. FSM design steps are discussed below. First, obtain the specifications of the circuit. Second, derive the states of the state machine and develop the state diagram. Third, develop state table from the state diagram. Fourth, decide on the number of state variables needed to represent all states. Choose the type of flip-flops for implementation. Derive next state logic expression to develop the logic input logic and output logic for implementation. And last, implement the design. The simplest sweet dispensing vending machine controller contains 3 major blocks as shown in the figure. These are coin sensors, vending machine, and sweet release mechanism. Let us now talk about the function of each block. The coin sensor system has 2 different input slots, one for inserting 1 rupee coin and another slot for inserting 2 rupees coin. The coin sensor generates 2 outputs, ORC for 1 rupee coin and TRC for 2 rupee coin. The vending machine has an arrangement for stack of sweets. This vending machine controller has 2 input ORC and TRC. In addition, the internal control circuit requires reset and clock input. The controller generates an open command for sweet release mechanism. The mechanism is designed so that it dispenses one sweet packet as soon as open command is received. Let us now implement the vending machine. Step 1. Let us talk about state diagram. While designing the state machine, it is possible to create a state diagram graphically to represent different states and how they interact. Let us now use state diagrams, the design frameworks for the state machines. The state diagrams make it easy to develop and understand the functionality of the application that uses a state machine. The figure below is an example of state diagram for a simple vending machine. The oval represents the states and arrows represent the possible transitions between the states. All applications require an initial state or starting point followed by transition state that performs different actions. A terminal state or ending point is a final state executed and performs complete action. State diagrams are useful in simplifying the design process of the application. Imagine a vending machine that accepts combinations of 1 rupee and 2 rupees coin to get a sweet packet. The cost of sweet is 3 rupees and the machine does not return change. First, establish the states that the vending machine might be in. ZR is equal to SA, that is a start state where no money is inserted. 1R is state B where 1 rupee coin is inserted. 2R is state C, where 2 rupees coin is inserted, and 3R is state D, that is done, that is 3 rupees are inserted. Now let us find about the possible ways or path that the vending machine can take to get into these states. Considering all possibilities, how the vending machine starts in the initial state. ORC, that is 1 rupee coin is inserted, TRC 2 rupees coin is inserted, default nothing is inserted. From this list, it is clear that there are 4 states and 3 possible paths from each state. It is now needed to depict which states are connected by which paths. For example, when vending machine is in the initial start state SA, the total change inserted is 0 rupees. When a 1 rupee coin is inserted, the vending machine must go to state B. Therefore, the start state SA leads to state B by the ORC path. By considering all the states and paths, it is possible to create a state diagram for the vending machine as shown here. With a state diagram, you can better understand how to create a state machine. Let us prepare a symbolic state table which includes present state, next state along with inputs and outputs. We can fill the state table from the state diagram. For example, present state to next state transition depends on inputs. Thus, there are 4 possible transitions with TRC and ORC inputs, as 00 generates self transition, ZR 01 results in state transition to 1R, 10 results in state transition to R, and 11 is not allowed, hence X. We can simplify the diagram by using the similar method, and similarly we can prepare other rows in the state diagram. Let us now move to encode the states. Consider the following substitutions in the state table. ZR is equal to SA is equal to 00, 1R, that is state B, is equal to 01, 2R SC is equal to 10, and 3R SD is equal to 11. Note that this substitution is not only in the present state but also for the next state as well. Next step in FSM design is to prepare K maps for D1, D0 and outputs. Here D1 and D0 are the inputs of the D flip flop and output is the final output of the vending machine. It is K map of 4 variables S2, S1 and Q1, Q0. After mapping the terms, it is clear from the map that it is possible to form 3 groups, 2 octets and 1 chord. This results in simplified Boolean expression D1 is equal to S1 plus Q1 plus S1 into Q0. Let us now prepare K map for D0. After mapping the terms, it is clear from the map it is possible to form the chord, and there are 4 chords those are possible. This results in the simplified Boolean expression as D1 is equal to Q1 S1 OR with Q1 S2 OR with S1 bar Q0 OR with S1 Q0 bar. Let us prepare a K map for output of FSM. After mapping the terms, we get 1 chord. This results in simplified Boolean expression for output as output is equal to Q1 into Q0. Next step is to realize the logic diagram from the 3 Boolean expressions obtained from inputs of D flip flop and output of vending machine. This implementation requires flip flops and combinational circuits as shown in this figure. Mainly to implement product term and the sum terms, simple AND gates and OR gates are used respectively. Let us now talk about the case study of traffic light control system. Consider a situation where traffic is to be controlled at a junction of main road and side roads. Main road has heavy traffic and a side road has less traffic. At a time, only one road traffic will go in all directions. Diagram indicates a square indicating main road and side roads. There is a one traffic light indicator system consisting of red, yellow and green color lights on each road as indicated in this figure. Let us now prepare a state diagram to describe the sequence of operations. In the first state, the main road light is green and side road light is red for 60 seconds duration. In the second state, the main road light is yellow and side road light are red for 5 seconds duration. In the third state, the main road light is red and side road lights are green for 60 seconds. In the last state, that is fourth state, the main street light is red and the side road lights are yellow for 5 seconds. The process is repeated again and again to generate the proper traffic light control. As there is a requirement of 4 steps in traffic light sequence as described earlier, the state machine can be implemented by using 4 separate states, namely S0, S1, S2 and S3. S0 represents the code for state first 00. S1, the code for this road is 01. S2, the code for this state is 11 and the code for S3 state is 10. The state or self transitions are depend upon the TL, that is long duration time of 60 seconds and TS, the short duration time of 5 seconds. Based on the state diagram, let us construct the block diagram for traffic light control system. There are 5 simple blocks consisting of combinational and sequential circuits. The first block in the traffic light controller is a sequential circuit. This sequential circuit requires 2-bit state machine to implement 4 states. The binary code generated by the circuit is 00, 01, 11 and 10. The sequential circuit requires a timing circuit to generate long duration timing of 60 seconds and a short duration timing of 5 seconds. This circuit can change the state according to the clock signal. The timing circuit has 3 outputs, TL, TS and clock. The timing and trigger inputs to the timing circuit are obtained from the third block, that is a combinational logic circuit. This logic basically generates the necessary present states, next states, output and trigger logic signals. It also generates logic high, logic low signals to drive the R, Y, G lights of both main as well as side roads. The interface circuit is basically used for driving the lights. Last block is a group of all traffic lights and their necessary wiring circuits for proper operation of traffic light control signals. If a side road vehicle occurrence is very rare, then a sensor can be put on sideway. When the sensor detects the presence of vehicle, then only side road will be given a green signal, otherwise side roads will always have a red signal. Yellow is used as a warning signal between red and green and vice versa. But in our country, yellow comes only after red and green comes directly. Let us now consider the last case study of tablet filling system. Tablet filling system consists of 4 sections. First, the first section is logic section to decide the number of tablets per bottle. The second section is tablet filling system. The third section is comparator for comparing present number of tablets with the set value of number of tablets per bottle. The last section is for the display of total tablets bottled so far. The tablets are fed into large funnel like hooper. The narrow neck of the funnel allows only one tablet at a time to fall into bottle on the conveyor belt. The digital system controls the number of tablets going into each bottle and displays continuously updated total near the conveyor line. The optical sensor at the bottom of the funnel neck detects each tablet that passes and produces an electrical pulse. This pulse goes to the counter and advances it by one count, thus at any time during filling of the bottle. The counter contains the binary representation of the number of tablets in the bottle. The binary count is transferred from the counter on parallel lines to the B input of the comparator. A preset binary number equal to the number of tablets that are going into each bottle is placed on the A input of the comparator. The preset number comes from the keyboard and associated circuits, which include encoder, register A, code converter A. When the desired number of tablets is entered on the keypad, it is connected and then stored by parallel register until a change in quantity of tablets per bottle is required. Suppose, for example, that each bottle is to hold 50 tablets. When desired number reaches 50, then A is equal to B. The output of comparator goes high, indicating that the bottle is full. The high output of the comparator immediately closes the valve in the neck of the funnel to stop the flow of tablets, and at the same time it activates the conveyor to move the next bottle into place under the funnel. When the next bottle is positioned properly under the neck of the funnel, the conveyor controls the circuit, producing a pulse that resets the counter to 0. The A is equal to B output of the comparator goes low, opening the funnel valve to restart the flow of tablets. In the display position of the system, the number in the counter is transformed in parallel to the input A of the adder, and B input of the adder comes from parallel register B that holds the total number of tablets bottled up through the last bottle filled. For example, if 10 bottles have been filled, each bottle holds 50 tablets. Register B contains binary representation for 500. Then when the next bottle has been filled, the binary number for 50 appears on the A input of the adder, and the binary number for 500 is on the B input. The adder produces a new sum of 550, which is stored in register B, replacing the previous sum of 500. This is how the tablet filling system works, and the whole system is under the control of the digital system consisting of combinational and sequential circuits. Let us summarize the key points we have studied in the system applications module, which is basically the last module in the series of digital electronics. In this module, we have applied the knowledge we have gathered in previous all modules, starting with how to use Boolean algebra for implementing the simple Boolean expressions. We have studied how combinational logic can be used to implement some of the simple logic circuits. Similarly, we have studied how sequential circuits can be designed with the help of state diagrams, state table and truth tables. In addition to that, we have studied the finite state machine and ASM chart. In this module, we have implemented the knowledge that we have gathered so far in almost all modules to put into several system design applications. The first system design application we have studied is a stepper motor controller system, where we have controlled the stepper motor angle as well as the speed at which the motor can be rotated. It depends upon the clock frequency and the angle through which it would be stepping in. The second application that we have studied is a vending machine controller system, where we have assumed that we will be inserting few coins and the sweets will be dispensed to the customer. So, this is another application. The third application is the day to day life application, where we encounter the traffic light problems. So, how the traffic light system can be designed, that is demonstrated through a simple application of a square, and basically there is a main road and the side roads. The longer time that is provided such a way that the traffic on one road will travel in all the direction during the long signal, whereas the short duration is provided for the transition from maybe green to yellow or yellow to red. So, there are two types of timings those needs to be generated, and that is demonstrated through traffic light controller application. And last and most important application that we have studied is a tablet filling system. In most of the pharmaceutical industry, we require certain number of tablets to be filled in the given bottle. So, we require a funnel wherein the tablets will be inserted. The funnel will allow only one tablet to be inserted into the bottle, and there will be a sensor which counts the number of tablets those are present into the bottle. So, naturally, while filling up the bottle, we will be counting a 50 number. Once 50 tablets are inserted into the bottle will be transported to the conveyor system, and then the next bottle will automatically come. So, how this automatic transfer of bottle is considered, that is implemented through tablet filling system. Thank you.